Hi, Assalamualaikum warahmatullahi wabarakatuh, my dear students. Today we are going to start chapter 3, Reaction Kinetics. And as usual, I'm your Madam Ruby, logging in for lesson 51, Reaction Rate. We are going to define reaction rate and explain the graph of concentration against time in relation to reaction rate. We should be able to write differential rate equation based on the reaction AA plus BB becoming CC plus DD. We will look at it later. We need to define rate law, order of reaction, and half-life. The Big Bang Theory is trying to explain how Earth exists at the beginning of time. So the Western scientists were trying very hard to deny the existence of God. For us, it's simple. God made all of this. So according to the Westerners, they said at the beginning, when the Big Bang happened, hydrogen atom exists first, and as it exploded, neutron and photon developed. So this reaction is very quick, very rapid, and it will form helium atom because two neutron combined. And then the remnants of proton turn back into hydrogen atom. So the same process happen again. As the rate of the reaction is lower, equilibrium is achieved. All elements assimilate to form the first organic cell in the sea and make up the Mother Earth. This is how the Big Bang Theory is developed to explain the existence of the Earth, the world today. But the thing is, if we look at our carbon cycle, oxygen cycle, nitrogen cycle, for example, carbon and oxygen, they are elements that are vital to life on Earth. Any excess in carbon would have prevented the formation of many material essential for life, because most of organic compounds are essential, are biological. And then an excess in oxygen would have burnt up many carbon-bearing biochemicals, which is also essential for life. So how can the Big Bang Theory say that all of this creation exists as a coincidence? We just believe that God made us. These scientists who believe in Big Bang Theory and the evolution theory, they actually are denying the existence of God. God has made us. Apparently, them making up these theories prove that their arrogance has no limit when it comes to admitting the existence of God. So in Surah Al-Furqan, sentence 2, Allah said, أعوذ بالله من الشيطان الرجيم الذي له ملك السماوات والأرض. We need only this phrase. He said, the one to whom belongs the kingships of the heavens and the earth. Everything in the heaven and the earth belong to him. He is the one that is the owner of the earth. Just now we were talking about how fast helium atom is formed during the Big Bang Theory, and when its concentration has increased, the reaction then becomes slower. This is what we call reaction kinetics. It's an area of chemistry concerned with reaction rates and the sequence of steps at which a chemical reaction occurs. So the study of reaction kinetics enables us to determine how fast a reaction takes place, to determine the conditions required for optimum reaction rates, and we should be able to propose a reaction mechanism after we have known this number 2 and number 1. Now, what is the rate of reaction? It's a change in concentration of a reactant or a product with time. The unit of rate would be mole per liter or molar per second. So the reaction rate is equals to the change in the concentration over time, which is equals to mole per liter or molar per second. Example, for a simple reaction A becomes B, the differential rate equation would be negative D concentration A over dt equals to positive D concentration B over dt. Because concentration of A decreases, concentration of B increases. This is another example. Now the reactants are A and B. The products are C and D. A in small letter is the stoichiometric coefficient, whereas A in capital letter is the element, the substance. So the rate of disappearance of reactants are known to be negative 1 over A, D concentration A over dt equals to negative 1 over B, D concentration B over dt. And the rate of formation of products are plus 1 over C, D concentration of C over dt equals to plus 1 over D, D concentration of D over dt. So the reaction rate or the differential reaction rate for the whole equation here would be written like this. For the reactants, it would be negative because it is disappearance of reactant. But for products, it would be positive because it is formation of products. Let's look at the graph of the concentration of reactants and products versus time, whereby we can see Rx is the fastest rate of reaction and Ry is the slowest rate of reaction. For reactants, the decrease of the concentration is rapid at the beginning of the reaction, and then it is going slow after some time and it becomes constant. For products, on the other hand, initially it is 0 because not yet formed the product is, and then it is going to produce product rapidly at the beginning, Rx, and then when the concentration has increased a bit, Ry is going on where the reaction is slower. Okay, as we are reading about Rx and Ry just now, the place where the rate is in the graph is called instantaneous rate. It's a reaction rate calculated at a specific time. So instantaneous rate is obtained only by graph of concentration versus time by drawing a tangent to the curve at that particular point. So let's look at one example of a reaction of a bromine liquid react with methanoic acid to become 2Br minus aqueous plus 2H plus aqueous plus CO2 carbon dioxide gas. So this is the concentration of the reaction of the reactant Br2 versus time, whereby we want to know the instantaneous rate at 100 seconds. So we cannot look at the concentration of Br2 here, but instead we have to draw a line tangent here, and then we are going to get the rate. The rate here is 2.96 times 10 to the power of negative 5 molar per second. And then what is the rate at 200 seconds? So you point 200 seconds here, and then you draw a tangent, and then you're going to get the rate is 2.09 times 10 to the power of negative 5 molar per second. And then the rate at 300 seconds is 1.48 times 10 to the power of negative 5. How do we get this value? Is by using the formula of differentiation. Negative d concentration of Br2 over dt. This means it is negative concentration of Br2 final minus concentration of Br2 initial divided by the difference in time. Okay. All right. Let's look at the differential rate equation step by step. For stoichiometrically simple reactions such as A becomes B, we have done this. Rate equals to negative d concentration of A over dt equals to plus d concentration of B over dt. The minus sign indicates the concentration of A decreases, whereas the positive sign indicates the concentration of B increases. And for the reaction that has stoichiometric coefficient 2A becomes B, the differential rate equation would be equals to negative 1 over 2D concentration of A over T equals to plus D concentration of B over dt. So here, 2 mole of A disappear. For each mole of B that forms, the rate of disappearance of A now is twice as fast as the rate of appearance of B. Let's do example 3.1 together. The question is, the formation of ammonia is given by the equation below. N2 gas plus 3H2 gas becomes 2 mole of ammonia gas. Write the differential rate equations for this reaction. Now the solution is you need to show that the disappearance of nitrogen gas is having a negative sign in front of the differential equation. So negative d concentration of N2 over dt equals to negative 1 over 3 because 3 is the stoichiometric coefficient for hydrogen gas. So negative 1 over 3 d concentration of H2 over dt equals to positive. Now this time it's positive because ammonia is going to appear. 2 is the stoichiometric coefficient for ammonia. So this is 1 over 2 d concentration of ammonia over dt. This equation means that the rate of disappearance of N2 is 1/3 of the rate of disappearance of H2 and half of the rate of formation of ammonia gas. Question 2. Consider the reaction 2HI becomes H2NI2. Determine the rate of disappearance of HI when the rate of I2 formation is 1.8 times 10 to the power of negative 6 molar per second. So the first thing that we need to do is write the differential rate equation as shown to you here. And then we write down the information that is given in the question. Rate of I2 formation is 1.8 times 10 to the power of negative 6. So this is equals to d concentration of I2 over dt. Now, here, this is equals to half of HI. So, negative half of d concentration HI over dt would be 1.8 times 10 to the power of negative 6. Therefore, the concentration of HI over dt would be 2 times 1.8 times 10 to the power negative 6 equals to 3.6 times 10 to the power negative 6 molar per second. So this is 1.8. 2 goes up here. We multiply by 2. The negative stays here actually because this shows that it is the rate of disappearance. Let's do practice 3.1. Based on the two questions of example 3.1, you should be able to do practice 3.1 on your own, and we will discuss it in tutorial classes later. But now we are going to move forward to rate equation or rate law. What are they? It's an equation that relates the rate of reaction to the concentrations of the reactants. For a general reaction that we have here, AA plus BB becoming CC plus DD, the rate law rate equation takes the form rate is directly proportional to A to the power of X, concentration of B also to the power of Y. Or when we want to remove this symbol, we are going to replace it with equals to K, whereby K is a constant. So it becomes rate equals to K, concentration of A to the power of X, concentration of B to the power of Y. X and Y is not a stoichiometric coefficient. It has to be determined experimentally. So for rate law here, concentration of A is in molar, B also concentration in molar, K is the rate constant, X and Y is the order of reaction for A and B respectively, whereby X plus Y would be the overall order of reaction. So with that, let's look at practice 3.1 question number 2. I just want to show you how to answer this question. Write the rate law for the reaction above. So this is the reaction that is given to you. 4 ammonia plus 3 oxygen gas becomes 2 nitrogen gas and 6 water. So how do we write the rate law for the reaction above? We are going to put the reactants only. So the reactant is NH3, the concentration of NH3 to the power of X. It is not to the power of 4 because X is not the stoichiometric coefficient. It's the order of reaction. And then the second reactant is O2. We put here the concentration of O2 to the power of Y. Rate equals to K, concentration of ammonia to the power of X, concentration of O2 to the power of Y. This is the rate law, and we're going to look at this even deeper afterwards. Right, we've talked about order of reaction, X, Y, Z. What are they? It's the sum of powers to which reactant concentration is raised in the rate law. The value of order of reaction must be determined experimentally and normally are integers and have the value of 0, 1, 2, or 3. For example, here we have an equation of F2 gas plus 2Cl2O2 gas becoming 2FClO2 gas. So the rate of law is equals to K, concentration of F2 to the power of 1, ClO2 to the power of 1. So notice that ClO2 here is having y equals to 1. The order of fraction is first order, and it is different from the stoichiometric coefficient over here. So the order of fraction is not related to the stoichiometric coefficients of the reactants in the balanced chemical equation. Okay, now let's look at the units of rate constant K. Let's say we have A becoming products. We don't need to know what the products are because we're just going to use the reactant. So the rate law would be K, concentration of A to the power of X. The units of K now depend on the overall order of fraction. So we're going to look at 0, first and second orders. The first one is zero order reaction. Let's say we have the rate law, rate equals to K concentration of A to the power of 0 because it's zero order reaction. Therefore, rate is equals to K because A to the power of 0 is 1. Therefore, the unit of K is calculated to be the unit of rate, which is mole per liter per second or molar per second. For first order reaction, let's replace the 0 just now to become 1. So the rate law is equals to K concentration of A to the power of 1. So we want to know the unit for K. So we put K in front as a subject. Therefore, rate is divided by the concentration of A. So what is the unit here? Molar per second, divide by molar, and we are left with per second. Next, we're going to look at second order reaction. Let's replace X with 2. Now K is equals to rate over concentration of A to the power of 2. Let's put the unit molar per second over molar square. So now we get the unit K for second order reaction is per molar per second. Let's do example 3.2. The reaction below is first order with respect to iodide ions and two thiosulphate ions. This is the equation, and the question is write the rate equation for the reaction. So the answer would be rate equals to K, concentration of thiosulphate ion to the power of 1, and concentration of I minus iodide ion to the power of 1. And the next question is, what is the unit of the rate constant? So, like what we did just now, we need to put K as the subject here. K equals to rate to the power of all the reactants here. So, rate is molar per second, and the concentration of thiosulphate ion and iodide ion are molar square. So the unit of K here is calculated to be per molar per second. For zero order reaction, the example of only one reactant A becoming B, when a reaction which is zero order with respect to reactant A means that the reaction rate is not influenced by the concentration of the reactant. Let's look at the rate law. Rate equals to K concentration of A to the power of X. So the rate equation or the rate law for zero order reaction is rate equals to K concentration of A to the power of 0. Rate equals to K. For first order reaction, what are we going to have is, again, for only one reactant, a first order reaction with respect to a reactant A is a reaction in which the rate of reaction is directly proportional to the concentration of A. If the reactant is doubled, the rate of reaction is also doubled. So the rate law for the first order reaction would be rate equals to K concentration of A to the power of 1. First order reaction is when we have rate equals to K concentration of A to the power of 1. This order of reaction is with respect to A equals to 1. Let's say we have A naught. This is the initial concentration of A is equals to 1 molar. Rate 1 is K concentration of A to the power of 1. This is first order reaction. Okay. And now we know that concentration of A is 1 molar given here. So we put 1 molar here. Now, what if we doubled concentration of A from 1 to 2 molar? So the rate 2 is Ka to the power of 1. Now A is double, it becomes 2 molar. So rate 2 now is 2 times of rate 1. Thus, doubling the concentration of A will double the rate of reaction. This reaction is first order with respect to A. Next, we look at second order reaction. A second order reaction is a reaction in which the rate of reaction is proportional 1 to the concentration of 2 reactants or 2 to the square of the concentration of a single reactant. Example of reaction is, let's say we have A plus B becomes product. The rate law is K concentration of A times concentration of B. Or A becomes product. The rate is equals to K concentration of A to the power of 2. So if we choose the second one here, using only one reactant, the order of reaction with respect to A is equals to 2. Say the rate 1 is K 1 molar square. When A is doubled from 1 to 2, rate 2 now is 2 molar square, means it is 4. 4K. Right. What happened here is, doubling the concentration, the rate will increase by a factor of 4. This reaction is second order with respect to A. Lastly, we want to know what is half-life. I'm sure you've seen this around in physics last year. Half-life is the time taken for a concentration of a reactant to decrease by half of its initial value. Thank you very much for watching, and we've done what we have to do for lesson 51. I will see you again soon. Assalamualaikum warahmatullahi wabarakatuh. Bye.